My friend wanted to put an altimeter on his RC airplane, and he uses Spektrum. So he could buy a $50 variometer from Spektrum, and that would work. But I decided that I wanted to try to make it myself. But looking at the manual for the Spektrum variometer, it looks like it's pretty decent, but $50 just seemed like a little bit much just for a fun little project that we wanted to try out. So um, after looking at the Spektrum XBUS telemetry data sheet, I guess you'd call it, it made it clear that this is just I squared C, and it'd be pretty easy to interface with. There wasn't a ton of information in here, as I mean, well, there was, but not of exactly how everything worked. So luckily, I found this guy, Raymond Domingo. He had already done this sort of thing by building it himself and using an Arduino, and I'm very familiar with Arduino, so I decided to go that route. But anyway, basically he kind of laid out that the receiver is 3.3 volt logic, and he was using an Arduino Nano, which is 5 volts, so he had to use a level shifter. And then he put it in his plane, but then he also had the source code here. And the useful thing was that it explained that the data always gets sent in 16 bytes, even though a lot of the different types of things only use a couple of the bytes, but you always send 16 bytes and the starting address and stuff for each different thing. But anyway, so the code was very useful, and that helped me out a lot to kind of know what I was trying to do. So then I just needed to pick out an altimeter, and I got this from Adafruit. It's the BMP 388. It's very precise. I think it's 24-bit. But yeah, it worked out perfectly for what I was wanting, and plus I just love anything from Adafruit, so picked that up. And then I wanted a small microcontroller as well, so I got a couple of these. I bought them off Amazon, but they're cheaper getting them directly from Seed. And yeah, I really like this little board. It's really tiny, and it's got a USB-C and castellated pins. But it's a Cortex M0 processor. It's got a 32 kilohertz crystal built into it as well. So anyway, yeah, it was really great, and it has a lot more pins than the Adafruit M0 Trinket. Now let's get the software sorted out. So again, I used this Raymond Domingo's source code, and I kind of followed along to figure out what he was doing with it, and then I wrote my own version of it. But his code really helped out a lot, so I'd recommend taking a look at it. I did make my own xbus.h file from the Spektrum manual, and I just copied all of it out of there, and then I had to delete a bunch of the different pieces because it's just copying it out of a PDF. But then you can see the altimeter code here has its identifier, and then the secondary ID, and then altitude and max altitude, and it's an int 16 and 16. So that's the main thing that we needed to know for how to structure our data. You can see the variometer, which you can buy from Spektrum, has this output. Now that I've got that, then I can tell it that I make the structure to hold the data, and I'm using the Adafruit library for the BMP 388. Then I create a couple buffers for the data. Now I'll show you why I use two separate buffers. Because basically the I2C request event, it's interrupt driven, so it could happen in the middle of writing data out to the buffer or something. It's not very likely, but it can happen. So I made a double buffer, and it just alternates which buffer it reads from based on which buffer is available. And then it also writes to the LED to kind of make it flash as it's getting read from, so we know that data is being transferred. The resetting starting altitude, I did put a button on the altimeter so that we can set it back to 0. And then now for reading the altitude data, just pulling it from the sensor, we read out the altitude given the just base sea level pressure, and we get a raw altitude. Then we also need to correct for it based off the starting altitude. So whenever you first plug in, it reads quite a few samples and figures out what 0 is, and so it gets the relative altitude from wherever you started. And then if that current altitude is greater than the max, then sets the new max. Now this is the starter script, and so you can change this counter to however many, but I noticed the first, I don't know, handful of samples was not very accurate, and so it took time for that filter to get engaged that's inside the BMP 388. So I went ahead and I put a counter, I think it's at like 100, and then it counts down so it reads 100 samples. Once 100 samples have been read, it does the reset starting altitude, and then it starts saving the data. And we also print this out. I don't actually need this, but it's nice to be able to plug in with a USB cable and see if we're actually getting data out. You can see in the save, we write to a different buffer each time. So every time that we save, we go ahead and just write to either spec data 1 or spec data 2. And then I do a memset to clear out the existing data and set the first byte to whatever that address is. In hex it's 1, 2. So start to send the starting out, or the ID, and then the secondary ID, which would be byte 1. It's always 0, so we don't need to reset it. But then if the starting altitude has been set, so if that counter has dropped to 0, so 100 samples have been read, then we can go ahead and actually save the data. Otherwise, it just sends zeros, just to make it nicer on startup. And then once the data is written, then the write buff boolean is flipped. So then we know we can pull from the other buffer. Alright, and then setting up the I2C just assigns this to the on request, and we begin with the client address for I2C, which again was 012. And then setting up the altimeter, we set it up for drone navigation according to the BMP 388 datasheet. And I also went ahead and added this in, that if it can't find the sensor, then it will just alternate the LED. So we can kind of know if we're not getting any data, then maybe there was a loose wire or something. Yeah, we also make sure that these values are initialized. We could change that to whatever, because I did have this set to like 1,000 just to see if I was getting data through before we knew that it was working. But again, these values are straight out of the data sheet, and I didn't really pick them, but it seemed to be working fine for me. And then it prints that it's ready. Now for the setup, we set up the output and input pins, and then I set this pin here because I noticed that the microcontroller was having a hard time starting. So I'll talk about that in a second, but basically this was to indicate that we started running the setup routine, and then at the end I pull it low, so then I can use an oscilloscope and measure from when the power started, or when the power was applied, how soon after I see that pulse of starting and then being done with setup, and how long setup started, or how long setup took to run. Also, I attached this interrupt to the button pin, so that's what resets the starting altitude, and it resets it once I release the button. The button has pull down resistors on it, so it's active high. Alright, and then all I do in the loop is read altitude data. And again, whenever I first start after the setup, it's going to read the altitude data and then be delayed by 20 milliseconds, and then it'll just keep on reading altitude data until all the packets have gone, or it's read 100 samples. And then after that, it will actually start outputting real data from the sensor. But that happens pretty quick. It's only a second or something. I was measuring the signal with an oscilloscope, which if you're a student, then I highly recommend buying a USB oscilloscope like this Analog Discovery. I got one whenever I was in college, and it has been great. I know $400 seems a bit steep, but if you are a student, you can get academic pricing. And whenever I got my the first one, and the Analog Discovery, it was $100 for a student, and I mean that's very reasonable. And this thing is awesome. It has saved me so many times, and plus it's small, it's portable. It's been great for all my projects, so I highly recommend it. But anyway, so from power on, we are discovering that it I put one of the probes on the voltage on the power supply, and then also on that ready pin on the microcontroller to see when it was actually getting set high, and that like pulse to say that we were in setup. And turns out it was taking 2 or 3 seconds sometimes, it seemed like. So I realized, oh, well, we need startup to be faster. This is an M0 processor, and so it's 3.3 volt like data and on all the pins, which is the same for the Spektrum telemetry data. I measured it with an oscilloscope just to be sure, but anyway, we found out that it's 3.3 volts on the pin, so then since I'm using this microcontroller, I did not have to use a level shifter or anything when plugging into it. But I first, like once I got the little board flashed and got the sensor connected, and I went ahead and I plugged it into the receiver through their telemetry bus, then things weren't working. Turns out that it was the microcontroller starting too slow. Spektrum starts the receiver, and then about 350 milliseconds after power on, it asks for all the telemetry devices on the I2C bus. So it just goes through every address and sees if they're present. So it does kind of a discovery thing at 350 milliseconds from power on. But what I was finding was the microcontroller was not starting in time, so we were missing that check-in. And if it misses the check-in, then the receiver never asks for any more data from that device. But if I powered on with USB first to the microcontroller and then powered on the receiver, then everything was working just fine. So it was just simply I had to increase the startup time, or I guess decrease the startup time. How do you make startup faster on a microcontroller? Well, so there's the Arduino bootloader, which does take some time, and some of them say that it has to be there's a double press logic inside the bootloader to see if you click the reset button twice, and that alone is 500 milliseconds. So my first step was to remove the bootloader, which I got a programmer from Adafruit. This programmer at $20 is very reasonable, and it works great. Adafruit has a great tutorial of exactly like how to connect up to an M0 board, and they use their Trinket M0 and a couple other boards that they have. And yeah, I followed the guide, and it really helped. So, but the first thing was figuring out how to compile the Arduino code without the bootloader. So in this case, I finally got it that I made a board. So again, I was using the seed board and XIAO with no bootloader. But selecting that board tells the compiler to not link it with a bootloader. So I went into the boards file, and you can see I made a copy of it before I started. But this is down inside your app data, local Arduino 15 packages, seed Arduino, hardware, SAMD, 1.7.7, which is just my version that I happen to be using, and in the boards.txt file. So this is where Arduino reads and finds all the different configurations of the boards that you have. So in this case, I went ahead and I just copied the XIAO first, like the one that came with everything, and I copied it down to here and called it no BL, or NBL, which is no bootloader, and named it no bootloader. So the things that I changed though from the original, I set the upload offset to 0. I'm not sure what that does, but in this case I don't think it actually applies to here. And then I also set the linker to use flash without bootloader. The flash without bootloader simply shifts all the logic, all the output down to 0 in the memory space. Normally it gives a gap for the bootloader to actually live in the memory at the start, and then shifts your application code down. So flashing it without the bootloader, that just moves all your data up, and that way your code will start right away instead of having to run through the bootloader. You can see here that this is flashing without the bootloader, and this is flashing with the bootloader. So the main difference is that whenever you flash with the bootloader, it adds this 2000 to the start and then subtracts it off the end. So that's really all that it's doing, but that's important because if your code, if it jumps or it does anything, then it needs to know where the addresses are, so you can't just shift that data around in the memory space. Now that you have that set, then you can go ahead and try to compile your code, and to do that you can go to Sketch and you can do verify and compile. You can also do export compiled binary, but it's up to you. If you do verify compile, then it will output your .hex file, a .elf file, and the .bin file in a temp directory. But if you do export compiled binary, it'll show up in your project folder. So if we do the verify compile, and now it is output the program into this temp folder. So you can just copy that. And you have to delete the slashes, the extra slashes. Alright, and then now you can see here are my output files. Now, a hex file, you can see has these addresses. And so you want that to be starting at 0, and if it was compiled with the bootloader, it would start at 2000 instead. Anyway, so the binary file, though, is the exact same as far as the data goes, but it doesn't have the addresses of everything in front of it. So that's why there's a size difference between them. But the nice thing about the hex file is that since it has those addresses, you know that it's getting written to the correct spot. Because I did try the binary files writing to address 0, but when I was compiling with the bootloader, it didn't work. None of the code actually worked. So it's just good to know. But anyway, then you can use Atmel Studio to flash it, and um, or, like I said, Adafruit has a great tutorial on how to do that. Um, so I went ahead and I flashed it with the .hex file, and then I plugged in power and waited for it to start. But I noticed it was still taking about 2 seconds to start. Now, this may be different if you use a different board, but turns out that the XIAO, one of the things that the developers did to try to make your life easier was they put a crystal oscillator on there for you, um, which they did to try to make the clock more accurate and more stable, and that's great and all, but it turns out this crystal oscillator takes about 2 seconds to start from power up, and that is just way too long for me. And in this case, we needed to start up right away, so the only option was to use the internal clock. If you're using something like the Trinket M0, you would not have this problem because they don't have an extra crystal. They just use the internal one on the processor. So that's what we need to do for this board. So for the no bootloader thing, we can go back to the boards file. And the other thing that I added in was this D crystallis, or -D crystallis, into the build extra flags setting. So basically that just says use the internal crystal. It doesn't have an external crystal available for the clock. And that makes the chip start up almost instantaneously. So whenever I started up the chip, again with the crystallis setting and no bootloader, then the yellow line here, and this was all measured in waveforms. It's the analog discovery software. Um, but basically you can see power on here on the channel 1, the yellow line, and then channel 2 is the ready pin, the output from the microcontroller. So you can see from here to here was around 10 milliseconds. So it took about 10 milliseconds from power on to where that ready pin was set high. So setup was starting. And then after that, it took about 3 milliseconds to finish setup, and then for it to go back low. So all in all, it took about 13 milliseconds to actually power on the chip and start running my application code. So in that case, 13 milliseconds is just fine for us. But yeah, again, this analog discovery software is really great. This isn't like a paid promotion or something, but I highly recommend anyone, if you don't have an oscilloscope, to definitely get one. Then now you can see the lights flashing, indicating that telemetry packets are being sent. All right, and then now it's flashing rapidly, saying that telemetry packets are going. And you can see as I raise it up, it goes up, and as I lower it, it changes. But using the button on board, I can reset the value to 0, and then there it goes. And then now that the board is powered up without the barometer attached, then it's just blinking on and off, indicating that it's not getting any data. And the telemetry is...
shows -0.3.